So I'm going to talk about the Inner Shell Spectroscopy Beamline ISS, about its journey. But before I run out of time, I want to acknowledge the support from all those people, both NSLS-II and our users, a very long list of people who supported different steps of the Beamline development and still support all the new features that we are adding. So thank you all, and thanks for coming to this seminar. Thanks, Jerry. I'm going to talk very quickly about the technical aspects of the beamlines, the data acquisition, what we have in terms of in situ infrastructure and sample environment, the UIs we are using. Going to go through two science cases that are close to my heart, and then I'll switch to high energy resolution work we're doing in the past year and a half, few of those preliminary results, and where we go with this with the new spectrometer designs. Okay, so ISS is a part of the hard X-ray spectroscopy and scattering program, which is 5 half beam lines with 3 hard X-ray spectroscopy beam lines, all located very close to each other. Not quite a diamond village, but close enough. We got at ISS the first light in April in 2016, and the following year we had the first general users, the first user publication, and then halfway through the first year of the pandemics, we went and enabled this high energy resolution work. And we've got a few science commissioning users by now that I'm going to talk about. All right, so what is that I want to tell you about the beamline that without boring you too much. The unique aspect of ISS and 2 other beamlines for that matter here is that we're using this damping wiggler as the X-ray source, which is actually a part of the accelerator to reduce the emittance of the beam. They are very good in terms of the, for spectroscopy, because they're covering a very large energy range, but they're a little hard to handle because the heat load of everything that this device spits out is in the range of 60 kilowatts, and we're only taking about 10% of this, but even this is 2-3 times more than other beamlines. So we had to deal with this in the design stage by special direct liquid nitrogen cooling monochromator and the water-cooled mirror, the first optical element. And it seems to be working quite well. We get resolutions that's not affected by thermal distortions of different optical elements, pretty much in line with the, the spectral resolution characteristics of the bending magnet equivalent. So, all right, very quickly going through the beamline, we have the first filter set here to take of the low energies for the different energy ranges, different thicknesses of the filter, the flat mirror, this internally cooled mirror, and the collimating mirror following this, the double crystal monochromator, the 111, and then the refocusing optics and the high harmonic rejection mirror in the end station. So the one component that we haven't commissioned yet that's very important in the context of high resolution is the 311 monochromator. But we are in the range of several 10 to 13 photons at this sample with the focused, with the unfocused beam. We cannot use the regular focusing solutions for the device that's so long, it's 7 meter long. So we're using this polycapillary lens for focusing into the beam of 100 microns, where we lose about 60% of the intensity, but this is still more than enough for many applications. And the energy range, just the standard thing, covering from titanium up to about 33. kiloelectron volt. So there is one sort of unique thing about our ability to control the monochromator motion. We have the full control over the velocity and acceleration, and we can simulate a traditional, so to speak, EXAF scan with slowing down the mono and accelerated it when it's needed. So we go, this is how we go through the regular EXAF scan, fast through the pre-age, slow through Zanes, and then accelerating it again in EXAF range. And we can go both ways. So that really gives us good control over the how we design the scan. So we can go, for good samples, for down to 1 second for a full EXAF scan, and a few hundreds of milliseconds for just an Zanes region. So the typical scan is in the 30 seconds range. All right. So also the unique aspect of our Beamline is how we do the data acquisition, and this is the scheme that was developed for ISS, but was adopted for another Beamline, and is now getting more recognition among other instruments at NSLS-II. Basically, we are not doing the synchronization in a regular way, like move to this energy and then take the readout of the detectors. We command all the detectors and all the relevant motions, just execute this trajectory. And then, since each of those readout modules, which we fondly call pizza boxes, they receive the signal with a very precise timestamp, with the GPS time signal, we can connect the different readouts. And from the encoder signal, which tells you where the monochromator is, and the analog signal from the ion chambers or diode detectors, we will then reconstruct the spectrum, which is this black line here, and then we bin it onto a regular, so to speak, EXAF, so Zanes grid. Okay, so those. I need to move the video bit somewhere so it doesn't obscure part of the slide. Okay, so what we can do with this is, like I said in one of the previous slides, we can record the full EXAF scan within the just a few seconds on good quality samples. Then it goes up to seconds to tens and sometimes hundreds of seconds for samples of very high dilution. But I just wanted to show you the comparison of our custom trajectory with the sine wave, which the camshaft monochromator would do. When we bin it, we get much higher noise here, and this is a 1 second scan. We get much higher noise in the Zanes region just because we are not optimized with this motion. Okay, so I want to go very briefly through some of the in situ things that we have, and having a Beamline that records the data in 30 seconds is a blessing. But if you compare it with a regular time scale of a catalysis or battery experiment, those typically takes minutes or even hours, or tens of hours sometimes. So there is no point to measure the data all the time. Because it increases the beam damage, and we need to leverage somehow this ability to record very quickly, but still utilize the most of the photons. And a lot of effort in our team and with the users was put into a high throughput sample environment design. And this is, for example, the system where we have 4 catalytic reactors inline, always individual flow control that we can just alternate and still follow the kinetics on the relevant time scale. And if you look at the next slide, we have a lot of those high throughput designs for electrochemistry, for batteries, but also some of the unique solutions for high pressure catalysis, the regular things, the setup we used for atomic layer deposition, I'm going to talk about at length a little later. And then obviously the instruments for gas analysis for catalysis experiments. So one of the things, I haven't finished this slide, I apologize. We have this gas handling system that we built quite some time ago, and it took us a while to bring it into operations, and we're hoping to have it fully commissioned sometimes later this year. We still, even without this, we still have the access to a lot of materials, a lot of gases and liquid vapors that are relevant for the for catalysis, for material growth, and we are approved to operate at relatively high concentrations if people want that. And eventually we want to get to this fast switching for modulation experiments, which is will be commissioned. So one important aspect of how our users interact with the beamline, our standard solution for NSLS-II beamlines is this Offutt Bluesky engine, if you heard about this. And it's a very powerful system, but it requires some scripting to develop the experiments. And we very early recognized that not everybody knows how to script in Python. This is why we developed and continuously add features to our own user interface that has access to all beamline operations, and it allows you to define the multiple samples, multiple points on the sample without much of a scripting. And so we can design long experiments without the need of typing something in the terminal, something like this. So it's pretty powerful. As far as the data visualization goes, we also built a tool that's based on it's called XView, that's based for data reduction on large, but it also handles very efficiently operations on very large number of spectra without choking on memory or anything of that sort. And we also added some of the data analytics tools such as PCA, MCR that I'm going to talk about. And that allows you to do this analysis in kind of real time, even as the data comes in. You find the principal components, the pure spectra from large data sets, and it really allows you to guide your experiment in the way you might not anticipate before the experiment is run. Okay, so what does it do for us? This control over monochromator and the data acquisition, this continuous data acquisition. We can run this trajectory multiple times and in a very short time between the cycles. And by this, we'll have access to very short time scales, such as seconds in this case, in a liquid state experiment where the ligand was added to a MOF metal organic framework suspension. And we could see this ligation or changes in spectra associated with ligation on, in real time. All right, we're using primarily a diode for the fluorescence measurements, just a regular PIPS, which is coupled with a filtering. We also have 4 elements SDD available. We're using it not as frequent as other beamlines maybe, because with that flux, it really easily gets overwhelmed. But even with the source, with the integrated detector, we can get a pretty good data out of very diluted sample. And I haven't calculated what it means in ppm, but for catalysis samples, it's pretty low concentration. And we still can get data on the time scale of the catalysis process. Okay, questions?
There are several. I'll start with one. Using the polycapillary on this very high flux source, do you observe any issues with damage of the optic?
That was one of the technical risks that we identified in the construction phase. And I'm very happy to say that even though, like, the polycap, the glass turns black instantly under the irradiation, its performance doesn't degrade on the timescale of a year.
Excellent. That's really good to hear. Matthew Marcus, you had a question?
Yeah, actually, he answered it. I was wondering about the use of energy dispersal detectors because it wasn't in your diagram, but in your last slide, you actually mentioned the 4-element and the.
I should have added that to the diagram, this branch of the trigger signal that goes into the SDD or any other, or Pilatus or any other detector that accepts trigger signal. So we have the timestamps for those frames. We have the frames, and then again, the post-processing, we cross-correlate it with the energies.
Yeah, I wasn't thinking of imaging detectors. I was thinking of, like, for instance, the SDD.
It's the same.
Yes,
it's the same from electronics perspective.
Okay, so you get a full spectrum at each trigger.
Right.
Okay, Wolfgang Kalib, you have a question?
Yes.
Hi, Wolfgang.
What's the maximum pressure? What's the maximum pressure in your gas sending system? How high can you go? 50 bar or?
We can go to 40 bar.
Okay. Yep, that's what industrial users sometimes want to have. Okay,
well,
thanks.
The problem with the industrial user, you say you have 40 bars, and they say, can you go to 100?
Yes, and when you have 100 bar, they want to have 120.
Exactly. It's a never-ending story.
Yep, thanks.
Very good. Konstantin, you have a question?
Yeah, thank you. How long the post-processing takes? I mean, when you record timestamps and then recalculate the energy.
It's almost instantaneous. I'm going to say for a 30-second scan, it's probably 2 seconds.
So the users see it live, the EXIF spectrum.
The users do not see it during the acquisition, but they see it 32 seconds after they started the measurements.
Okay, thank you.
All right, seeing no more questions, you should continue, please.
All right, so I was kind of questioning what I should be showing for the science examples, and we've been in the business for 4 years now, have over 100 publications, and everybody, in the EXIF's world, they know what kind of typical measurements the Beamline does. The catalysis, the battery work, the single atom catalysis is a big theme right now, and we've done quite a few high impact publications in this field. And I'm just not going to talk about this because everybody knows what this is all about. What I'm more interested to show you is what occurs at the intersection of this advanced XES measurements and data analytics. And I have 2 examples to show just that. So what we are integrating in our data analysis, and it becomes more and more of the inline thing, is the various data analytic techniques. And one of them is really helping us to understand the chemical system here. So here we worked with our team at Stony Brook battery team at Stony Brook that compared the process of lithiation and sodiation in the titanium sulfide batteries. And in a typical experiment, as you know, you create a spectral stack of different at different potentials, and then the analysis could be, oh well, this line has moved a little bit to the right, and this level of information is really not sufficient because it doesn't tell us much about the transformation of the chemical system under investigation. So what we are introducing more and more into various kinds of measurement is this technique called MCR, which is the method to extract pure response profiles or pure spectra with very little information of the of what those spectra are. And in the case of this, the lithiation, the MCR easily gives you two components, right? That you're in the charge and discharge. They're very easily recognizable, and we get a very good fit for the entire stack. Now, the good thing is now with the access to, say, material databases such as Materials Project, you can very easily pull out the structures and get the FEF calculations for them because it's already on the MP, or you can have the input file instantly for your own FEF measurement. Now, what happens in the case of the sodium? And the two components are really not sufficient for the fit. We need to introduce an additional spectrum, and we tried with the process with multiple contributions and concluded the three components are sufficient to describe the system through the charge-discharge cycle. And the interesting thing to see is that if you look at the phase diagram, there's actually a minimum in between the non-sodiated and the sodiated state. And this guy right here is the partially sodiated titanium sulfide. So let's see what we can do now. Again, we can pull the data for those three FEF calculations, and they're actually in a very good a match with the experimental data. It doesn't always work like this, but here we were just lucky. And the good thing is now we can design the next level of experiments, say to go into a multimodal direction, take diffraction, for instance, and we can look for a specific peak belonging to this phase, and indeed we identify this in this supporting experiment. So it's really, this data analysis is a very well-known technique which is only in the last decade because recognized in the EXAFS world, but it's really powerful, especially when you can do it on the fly, you know, when the user is still, when the data is still hot. All right. Let me talk about the next example that's describes a rather unusual experiment in terms of how we conduct it, which is the investigation of the growth by ALD of titanium oxide on zinc oxide nanowires. This is the image, SEM image of this nanowires, and the titanium oxide here is covering the zinc. So if you know how ALD works, you add the precursor, the organometallic vapor, to your substrate that absorbs, and then you add the pulse of water or oxygen to remove the ligand, and this is how you grow the material layer by layer, hence the atomic layer deposition. And the way how we are taking this data, the ALD happens on its own time scale, right? When the pulse needs to come, it comes. But then we have our own cycle of measurements, and I wanted to show you what kind of information we can extract from this. All right, so just from the kinetics of the growth, we can already recognize that there are three different steps. The stage 1, which is the nucleation on the surface, and the stage 2, which is normal linear growth, and the transition period in between them. So that's good. That tells us something about the mechanism of the process already. And if we now introduce this differential Zanes concept, which is nothing else but the extracting from this kinetics, extracting the additions after each cycle. What are the spectra that corresponding to the addition of the material from one cycle to the next? And if we integrate them or average them, those are the two spectra that we obtain from stage 1 and stage 2. And if you look closer at them, you see how this earlier step has a much stronger pre-age feature, which is an evidence for a lower coordinate titanium. Whereas the differential spectrum in stage 2 is really the bulk of titanium oxide. So now, this is the comparison of the final Zanes and this differential signal. Now we can apply the same MCR to the stack, and we are extracting two components out of this. There's MCR the bulk signal, and then the transient signal that kind of starts up and then almost doesn't go away with the progress of the process. And this is our signal from the surface or the interface, this under-coordinated titanium atoms that are in the very interface of the growth. And these are how they behave this is the fraction. It's just another representation of this picture. So we need two unique components to the in this process, and the thickness of the thin one is really lower than one monolayer. Now I want you to examine this picture because my eyes hurt when I look at this. But what I'm trying to show here is this detachment of the cycles. So this is the full ALD cycle. We're injecting the precursor here, and injecting the water there in the middle. But our spectrum, our monochromator trajectory, motion trajectory is not synchronized with this. But we know exactly how to correlate the different cycles with. So we're not looking at the entire spectrum, we're looking at the parts of the spectra now and process them separately. So now we can, one important thing is that ALD is presumably a self-repeating process. So every next cycle is exactly like the one before. And so we can essentially bin the data by delay time from the injection of the precursor. And you see this strong peak right here, which is essentially this precursor vapor that goes in and is pumped out, and whatever is left on the surface remains, which is this yellow component, which is not very pronounced, but that corresponds to just this region, which is 2 to 5 seconds after the pulse, when the gaseous precursor is gone. So we essentially can get a better time resolution from this process than the length of the scan. All right, and based on this, I don't want to go into the mechanism so much, but it essentially tells us the sequence of events that happen during the half cycle of the precursor and the half cycle of the water addition. Nothing from the titanium perspective happens in the water cycle. It's just that the ligands are being removed. But it really shows how this advanced processing and the data analytics helps you to resolve the those atomic structures that only occur transiently during the process. But of course, it's because of the self-repeating nature of the process that allows us to do that. All right.
Those are great examples. We'll start with a question from Matthew Marcus.
Yeah, I was wondering if the intense irradiation if it will affect the ALD process. Like, for instance, when you take the sample out, do you see a little spot where the beam was?
Mm-hmm. I can only say what my ALD experts are saying, who examined those films after this process, and concluded that there was structurally no damage. Structurally and chemically, there was no modification to the samples due to this being in the beam.
Okay, I was thinking it possible that for the flood of photoelectrons coming off the surface might affect the deposition, but I guess it doesn't. Anyway, it's quite impressive results. Thank you.
There is a plenty of examples where photoelectrodes play a very important role, very bad and important role. But yes, I chose to give you a good example.
Okay, with that excellent the confession, a question from Alexei Bubnov.
Hi, Alexei.
Hello, Eli. Thank you so much for these really nice examples on the presentation. One question was regarding why did you not synchronize the ALD cycles and the XAS acquisition? I mean, you have demonstrated very nicely that you can post-process this data. However, it's not that it's not synchronized, but why do you not start at an earlier stage? Is there any experimental reasons or any practical reasons that?
Okay, so again, a confession, I cannot do this. I cannot synchronize without much work the data acquisition or the motion controller for the monochromator and the ALD deposition instrument. But what I was trying to say is that I don't need to. I might actually gain from the ability to post-process the data having another stimulus. It could be this, it could be, say, in a catalysis world, it could be a pulse over reactant gas or something. I could just measure continuously and then take these bits and pieces and recombine them into the spectrum that corresponds to a specific chemical state. Not to say it cannot be done.
Okay, thanks.
All right, I have a question. The MCR, that was fascinating. How is that different than doing PCA with one principal component?
The PCA is the first step in the MCR analysis. I was here before we do the MCR, we need to constrain the number of components, right? And this is what the PCA does for us, or SVD.
So the first step is you realize, if I have the mean and one principal component, which adds or subtracts from the mean, then that covers what I need. And then the MCR figures out what that addition and subtraction is?
Yes.
That's really nice. I wonder if maybe that's been underutilized in Zane's analysis for many years. That's really quite an interesting twist on things.
again, if I had time, I could speak at length about the how careful you need to be with MCR, but again, focus on the positive.
I think
Yes,
I think it's true for all data science methods, how careful you have to be.
As I understand it, the difference between MCR and things like ITFA is that MCR kind of takes into account the sequential nature of the measurement. So it makes it so that you get the nearly, more or less continue, or at least a smooth evolution of loadings versus time. Whereas ITFA treats all the spectra as independent and disconnected from each other.
Matthew, it's an excellent remark. I want to say that indeed there is there's this assumption of kind of smooth transitions with MCR, but it doesn't mean you cannot treat the other kinds of data with this. For instance, there's work that Dennis Lesher, the Beamline scientist at ISS, has done with one of the users who had a large 100 spectra of cerium oxide that contained cerium-3 and cerium-4. And because we had, all the variations of this, we could stack those spectra so there will be like smooth transitions and identify the two components that were not quite similar to pure cerium-4 plus and cerium-3 plus.
Right. Yeah, I mean, this is a technique that's been used it's a chemometric technique that's been used in, for instance, for UV vis spectroscopy forever. But I guess it's just starting to be used for XANES.
I think that can be said about a lot of the data science methods. With that, I'm going to ask Eli to continue, please.
All right. How much time do I have, Jerry?
Oh, certainly 15 minutes, even 20 minutes if you have that. But 15 minutes would be great.
Okay. So now we talked about the traditional work up to now. ISS was designed to be a high energy resolution beamline, first and foremost, but we spent a big chunk of the first few years doing just regular XANES exhaust measurements. And now, since 2020, we are entering this realm of high energy resolution. That what it gives us compared to, as I said, the traditional spectroscopy gets us a much better sensitivity to the absorber ligand interaction. It gives us the access to low Z materials that are outside of the energy range of the regular hard X-ray torsion beamline. We're also, with things like RIXS, we're more sensitive to valence states and to all different electronic transitions in the material. So what are we doing about this? This is, Bruce is on the call. This slide, the next one was done with him or with the materials, Bruce Rival. So this is just to show you the kind of improvement that this is the HERFD, the high energy resolution fluorescence detection, where use, I'll show you the curved optics instead of energy discriminating detector or just regular fluorescence or transmission detector. This is a kind of enhancement that's due to the removal of the core hole broadening. Works especially well for 5D metals, but also gives you, as you'll see on the next slide, also for first row transition metals, it gives you a much better sensitivity to the pre-age features and the features in the white line. The other kind of early demonstration experiment was getting those very weak K-beta satellites, the K-beta 2.5, K-beta double prime, which are very, very sensitive to the neighboring ligands, because there is a mixing between this 3D levels and the ligands. And in this case, you can see how you can discriminate between the nitride and the nitrogen and the oxygen in the coordination sphere of titanium from measuring this, again, very weak transitions. So how it's done? It's done either with the spherically bent analyzer crystals that refocus the fan of emission onto the detector that's not dispersive or dispersive with some modifications, and they work very well for dilute samples. The von Hammes geometry, which requires a cylindrically bent crystal, is a dispersive way of doing the emission spectroscopy with the position-sensitive detectors. They usually require more concentrated samples. So all those preliminary measurements we were doing with just some semblance of the spectrometer, the motorized analyzer crystal, and the detector that's here somewhere. But even with this setup, and obviously with the helium chamber, something that Jerry was talking about in the beginning, this helium chamber, we could get very competitive data. And also it's compatible with some of the in situ work, in situ setups, and we are constantly adding new in situ instrumentation to this measurements. All right, so this the three examples, and I will go very quickly through them, but those are all our science commissioning experiments. So this particular example on the copper catalysts, which are ligated with those strange looking organic molecules, to me at least, and the different catalysts that do this one kind of chemistry but not another, and we're trying to understand what is the driver for reactivity and what is the origins of selective behavior on those catalysts. And this is, I'm not going to dwell on this, but those are the solution phase or liquid phase experiment. You cannot leave your solution in the focused beam of ISS. It will do chemistry on its own. So we developed a number of different jet sample delivery systems that allow you to work with liquid samples without subjecting them to immediate death. Yeah, so this, by just comparing the total fluorescence yield and the HERFD measurements, you can see the much sharper features here in the early in the white line for different of those materials. Some of them, two of them are inactive, two of them are more active as the catalyst. So let's see what we can get out of this. We can now do the deconvolution into Gaussians and just try to correlate those different contributions to the white line with the reactivity. This is, all of this is like, none of this is a complete story, because the analysis of this data is a little bit more convoluted than irregular Zanes, for instance, but we are trying. So in this particular case, we in this 1s-4p transition, we see that one of the components has actually a strong correlation with the activity. It's much more pronounced, and we are trying to do the molecular orbital analysis here on those samples. The other example is the electrocatalysis, where our users, many others, are trying to invent the replacement for noble metal electrodes, for oxygen reduction, for hydrogen evolution, all those things that are relevant for things like water splitting and artificial photosynthesis. This iron and C catalysts are pretty popular for this matter. They are usually done. They're usually prepared by pyrolysis of organic MOF, metal organic frameworks, in addition with the salts of the materials that and you get the sheet-like materials where the iron and copper is incorporated in those sheets of carbon and nitrogen. And again, by comparing the regular fluorescent data with the HERFD, we see better result changes in the cobalt veins that corresponds to this oxidation that during the electrochemical process that we were interested in. And those are the two different materials, the cobalt and the iron. And in one case, in the case of iron, the shift at higher potential is considerably larger, which is what we're trying to understand in terms of the reactivity. Those materials. I'm going to skip this slide probably. The last example is on the first demonstration of the user RIXS experiment with the team from Rutgers, who are also developing a photocatalyst for CO2 reduction and water splitting and all those popular topics these days. They discovered that the doping of their titanium based metal organic frameworks yields higher activity in the CO2 reduction. However, this molecular level understanding of what is going on is not there yet. So again, we can compare the just regular XES. You see there's very little difference in between the undoped and the doped material. But once you can resolve the same spectral kind of 2 dimensions, start seeing the features here that are quite different from the titanium, I'm sorry, the native material and the doped one, especially in the region that's associated with the delocalized states in titanium. And again, we have to bring theoreticians on board to get a better understanding of what we're actually seeing here. All right, so much for science. Now, as I mentioned before, we are doing this high resolution with a single crystal, with an ad hoc, so to speak, motion control. We've designed and built the 5 crystal, or at least the Johann spectrometer for 5 crystals, and we will be, this is what it looks like with the dummy analyzers. So it's already on the floor. We will be installing and commissioning this in the next month. We are going through the design process for 15 crystal von Hammes spectrometer with mechanical design almost complete. So we'll get in a year from now a very competitive instrument with 5 to 7 crystals, such as ESRF or SSRL or Petra 3 have. And ISS provides some competitive advantage because of the continuous scanning. We can do the same continuous scanning as I was describing in the earlier part of the presentation here with the multi-axis motion of the spectrometer. The one interesting development that again is led by Dennis is the tender X-ray spectrometer, which is again being designed in now the different parts. And this is going to serve our users that, together with the elements above titanium, are interested in the chemistry of sulfur, phosphorus, low line ages of 4Ds and 5Ds. This setup will cover this 2 to 5 kiloelectrovolts. We cannot go there to do resonance measurement, but even the non-resonance emission spectroscopy will be a huge help for those who are trying to learn something about those lighter elements or edges that are more sensitive to to changes in electronic structure. And we hope to commission this instrument sometimes in the summer or fall of this year. So here it is, coming to conclusion. We're in the full general user mode for XES. We have many different sample environments for in situ and operando measurements. We're a high energy resolution program is ramping up, and we really need the direction. We're open to suggestions. We are open to ideas as to, we do not have the full crystal library that covers all the energies, but we are very responsive in the way how we spend our crystal budget to address the requests from the community. So we need it. And the limits are on site users will be lifted come April or May. So we're looking forward to those complex and exciting experiments that are frankly not possible with this limited number of on-site experimenters. All right. And other than that, ISS is looking for a postdoc to work in the catalysis field primarily and the high resolution. So if anybody knows anyone who would be interested, please spread the word. And here I'll stop.
Very good. Thank you, Eli. That's terrific. Okay, good. You're not, I thought you were frozen for a second. All right. So first question, Professor Jun Kawai, please.
Yes, I have a question about the K-beta 5 you showed for titanium. So I have a question. Are there any correlation between K-age pre-age structure and the K-beta 5? Have you ever experienced something like that?
The difference between the
that means if the pre-age is strong, then K-beta 25 is also strong, and the pre-age is weak, and K-beta 25 is weak.
I don't think I have enough information to say if they're correlated or not.
Mm-hmm.
And I need to think a little bit more about the physics to answer it from fundamental perspective.
Yeah, maybe K-beta 5 is 1s 3p. It's buried in the 3D orbiter, but it's an electric dipole, and that means it's quite similar to the pre-age structure. So
Right.
maybe some relation, I believe.
We need to look closer into this. That's an excellent suggestion.
Thank you.
I have a technical question, and I'll remind people we have another minute or two for questions, so please type in a question if you have one. You're making that very nice 5 spherical analyzer spectrometer, and are you using it dispersive? First, are you using it dispersively or non-dispersively?
The first will be the non-dispersive way.
Okay. And then my second question is whether you've considered the importance of rotating the crystal analyzer about the cylindrical axis in order to simplify your energy tracking.
We have this motion.
You have not tilt, but rotation also in there?
Rotation, yeah.
Oh, how nice. I didn't see that. Okay.
Oh, I'm sorry. It's very difficult to see in this stack, but there are 2 angular motions.
Right, but I'm speaking of a third one, which is to rotate the lens, if you like, about its cylindrical axis.
Oh, about the cylinder.
Yeah, so what that does is it lets you remove the problem from the crystal miscut and makes it easier to track the Roland circle then. That's something I can tell you more about offline, and I think you'll find it very helpful.
I'm sure this is a very, it's important. We decided to exclude it for technical and budgetary reasons.
Right, but you don't need it to be active. You just need to do it manually once. And then after that, your energy tracking becomes much simpler if you have multiple analyzers with different crystal miscuts. Anyway, we can talk about it offline. I'm not seeing any other questions. We're at 10 o'clock.
Yes. I have one
Oh, please,
question.
yes.
So the just this spectrometer. So you measure the very weak lines, weak scattering lines or something, and then I have question: how is the stray light or something? Stray light is negligibly small, or something problem. This is my question. So that's my question.
I'm sorry, you need to.
He's asking about stray scatter. How are you rejecting stray scatter to make sure that you're getting the signal that you care about?
A lot of tinfoil.
Okay, so a lot of masking to prevent line of sight.
Right. So if you, I don't think there is any better.
Okay, but sometimes
you can see how the detector and the chamber is all covered with tin.
Sometimes we must measure very weak lines, and then the stray light of ppb intensity will interfere the very weak line measurement. I'm not sure, because I'm very old and my knowledge is about 20 years ago's synchrotron facility. So I'm not familiar with the present day synchrotron beamlines.
Unfortunately, there is very little invented in this department.
I'm going to disagree. I'm sorry. And the most important thing that's happened is you have pixel detectors now, which lets you select a very small detector region. And that by itself is a tremendous factor for rejecting stray scatter. So I think at least one very important thing has occurred in the last 20 years, which helps with these very dilute studies when you have strong backgrounds. I think that's very important.
Right. And the other thing that I mentioned on the slides, but I wrote on the slides, but didn't mention, there are detectors now with some energy filtering, to the 1 kilo electron volt. It also helps.